Part 1 of Magnets, Lesson 2. And we're asked a little recall question to remember back to Lesson 1. We're shown this picture. We've got a bar magnet and we've got some plotting compasses, and obviously someone has done the experiment and they've plotted out the magnetic field all around this bar magnet. So we see the lines coming out here from the north and going into the south as we expect. So describe the picture. So the picture shows the magnetic field around a bar magnet drawn using a plotting compass. Okay, and what are these lines called? These lines are called magnetic field lines. Okay, and why are the lines in this shape? So the lines show the strength and direction of the magnetic field. It is strongest at the poles where the lines are close together, and obviously weaker as we go further away from the magnet. The magnetic field strength is becoming weaker. Okay, right. So we know what this the magnetic field around the bar magnet looks like. We looked at this in the last lesson. Now we're going to try and think about how this would work if we had two magnets placed side by side. So here I've got a magnet where the north and the south poles are placed close together, and here I've got the north and the north pole placed close together. So we have to see, what do we think the magnetic field would look like around these bar magnets. So here I've shown the magnetic field drawn separately around each of the magnets. So this side of the magnets, the magnetic field lines are come right out from the north pole, go round and into the south pole, and likewise down here come out from the north pole, go round and into the south pole. But if we think about this part where we've got here, the magnetic field line is coming out and it should go round all the way around to the south pole here. But here we've got a south pole that's closer. So what will happen here is this will simply loop in like this. And likewise on this side, rather than going all the way around, this will simply loop in like that. So we get lines coming round like this and like this, from the north pole here to the south pole here, and from the north pole here to the south pole here, and then we will have some field lines going round like this. So on the outside of each magnet, same as before, but here we have these field lines joined together, the ones coming out from here and the ones going in here joined together, because this is the shortest distance between this north pole and this south pole. So you can see what's going to happen here is that, remember, the magnetic field lines are showing us the forces that are going to happen. So here we've got forces drawing these ones together and forces drawing these ones together. So the two magnets will be attracted together. So what's happening then in the case where we have the like poles? Well, again, on the outsides of the magnets, nothing's going to change. But when we look here, so here normally this magnetic field lines can come round and back into the south pole, and likewise should come round here and back into the south pole. But we see these lines are going in opposite directions. This one and this one, they're going in opposite directions. So they're going to stop their magnetic field lines from getting round to the south pole. And what's going to happen instead is that they're going to push each other off to the side like this. And the same on the other side. So what we have there is that rather than having an attractive force, here they're pushing against each other because they're both trying to go in opposite directions. So they're pushing against each other. So we get a repulsive force. Now remember, this is shown in the PowerPoint, so you can make sure you've got a nice sketch of the correct magnetic fields copied from the PowerPoint. Now, show how the right hand thumb rule can be used to show the direction of the circular magnetic field around a current carrying wire. So if I've got a wire and it's going up the page like this, what you discover is if you put some plotting compasses around this wire, they'll form a circle. The arrows would point in, one would point this way, the next one would point this way, next one this way, and the next one this way. Okay, and so the magnetic field forms a circle around the wire like that. Now, if I go slightly further up in the wire, again, I'll get another circular magnetic field like this, and below is the same thing. So at every point in the wire, we've got one of these circular magnetic fields formed around the wire if there's current going through it. So for the right hand thumb rule, so your thumb is the direction of current and the fingers is the direction of the magnetic field lines. So here's the wire that's going up. So holding with my right hand, my thumb is showing the direction of the current, which is upwards, and my fingers are curling around the wire like this, and they're showing me the magnetic field is going this way anti-clockwise around the wire, which is what shown there with the magnetic field going anti-clockwise around the wire. Now, the next task you were asked to do in the lesson is to draw the magnetic field around a wire. And here I've tried to show the magnetic field around the wire, but one of the problems is this is in 3 dimensions. So the wire is going up in the page this way. This magnetic field is coming in and out of the page. So I've tried to draw it there, but I'm drawing on 2 dimensions, so that's quite difficult to do. So to be able to show the 3 dimensions there, so we can see the magnetic field around the wire, what we do is we draw the wire to show the current either going into the page or coming out of the page. And if we say, so the circle here represents the wire, and by putting a dot or a cross into the circle, we show which way the current is going. So if the current's going into the page, we show that with a cross or an X. If the current's coming out of the page, we show that with a dot. Now this was shown in the PowerPoint. The idea is that it's as if we were looking at an arrow like this, and we're looking at it this way if the current's coming out of the page, and we're looking at it going this way if the current is going into the page. So looking at the arrow from the front, we just see a point. Looking at the arrow from the back, we'd see the cross of the feathers. Okay, so this is the current going into the page. So we need to show what the magnetic field will look like. I'm going to use my right hand. My thumb represents the current, which is into the page. My fingers are curling around in this direction, which means that the magnetic field is clockwise around the wire. And current coming out of the page, in this case, again, my thumb represents the current, and my fingers are wrapping around in the other direction. So the magnetic field is going anti-clockwise around the wire. Right, now the next task you were asked to do was to show what would happen is if instead of having just one wire, we have a coil of wire. So remember, what we're saying here is we have a wire that's been looped around like this. Okay. And we imagine this is our piece of paper like this. So the wires are going into the paper on one side, coming back out of the paper on the other side, and then going back into the paper and coming out of the paper. So the current, if it's going this way, would be going into the paper here, coming out of the paper here, going into the paper there, coming out on the other side. So that's what this represents here. We can see we have the current of the wire going in and out of the page, either shown with the cross or the dot. So what we can do is we can draw the same magnetic field around each of these wires as we drew before. So I've very roughly sketched the magnetic field around each of the wires. So what we can see is that here the magnetic field is pointing from right to left along here with the wires at the top, and the same with the wires at the bottom. The magnetic field is pointing from right to left. Here all magnetic field lines are pointing from left to right, and the same at the top here. But we can see that in between here I've got arrows that are pointing up and these arrows are pointing down. So because they're pointing in opposite directions, they will somehow cancel each other out. The magnetic field all pointing in the same direction inside, between the wires, inside the coil. That's showing that the magnetic field is going to be very strong inside the coil. That's because all of these arrows are going to add together. Now, why do the arrows add together? Well, let's imagine, remember, the magnetic field is showing us where magnets will feel a force. So if you imagine, if I had an object, and I drew a free body diagram, and this, it had a 10 Newton force to the left, and it had a 5 Newton force to the right, we would say that the resultant force is equal to 10 minus 5 equals 5 Newtons to the left. Because they're in opposite directions, we have to take them away. However, if the arrows are in the same direction, that one should be smaller. If the arrows were in the same direction, then we add them together, which makes sense. The forces are pulling in the same direction, so overall we get a larger force. So it's the same thing that will happen here. We will get a larger overall force because all of these arrows are pulling in the same direction. So we can draw what the combined effect of all these wires are. So we get lots of lines in the center, and then the lines loop around, go around the outside of the coil and come back in on the other side. Now this is something we've seen before. This type of magnetic field is something we're very familiar with. When we look back, this looks very, very similar to the bar magnet. So the outside looks exactly the same. It's just that because it's a coil, we can measure the magnetic field that's happening inside between the wires. So there is no difference between the magnetic field around a coil, and in this case we give it a special name which is called a solenoid. So a coil of wire with a current going through it generates a magnetic field that's identical to a magnetic field of a bar magnet. Furthermore, like all magnets, this now type of magnet that's been generated by putting current through a coil, like all magnets, this has got the north pole side where the lines are coming out and the south pole side where the lines are going in. Now this is shown in the PowerPoint. What we've discovered is that the solenoid has a magnetic field very similar to, well, the same as a bar magnet with the north pole and the south pole. We can also identify which side of a coil is the north pole or the south pole by looking at, so this is my coil and here is the current that's going into the coil, so it's going in round like that. Okay. So what way will the magnetic field, which pole will this be? Well, what we can do is we use a trick, which is, this looks vaguely like the shape of an N, so this is my north pole. Remember what this is showing from my diagram, the diagram we did here, is this is saying the current is coming up on this side, and it's going up on this side, and up here, and going down on that side, down there, and that gives us our north pole. And if it was going, if I drew it the other way around, so the current was coming out rather than going in, then what that would mean is that I would have my south pole. So, and that's shown because this looks a lot like a shape from there. So current going in like this, that's my north pole side. The current's coming out, that's the south pole side. Or we can draw out this diagram that shows us where the north and the south pole is. So here are some of the similarities and differences between a bar magnet and an electromagnet, which is what we call the magnet that's made using a solenoid. So some of the things that are particular to a permanent magnet is that the magnetic field is always on in a permanent magnet, whereas in an electromagnet, the magnetic field can be switched on and off. In the permanent magnet, the strength of the magnetic field can't be varied. So always got one strength, whereas in the electromagnet, the strength and direction of the magnetic field can be changed. And then the things that are the same, both the permanent magnet and the electromagnet produce their own magnetic field, so they're not induced magnets, and both have north and south poles with the usual rules for magnetic forces. So for the next task now, you need to make sure that you've looked at the video that was, the link was in the PowerPoint, showing how we can make and change the strength of an electromagnet. So there was an experiment described, and you need to answer these questions related to that video. So here are some of the things that were mentioned in the video. The lady used a nail. This is used as the core of the electromagnet. So the reason why you add a core made from some magnetic material is it makes the electromagnet stronger. There was a cell we used for the power supply, some insulated wire, and used that to make the solenoid, and paper clips to test our electromagnet. What she showed how to do was you wrap the insulated wire around the core, the nail, obviously always turning in the same direction, so you create the solenoid. You connect the wire to the battery, and then you check how many paper clips can be picked up. And one of the things you could do is to vary the number of turns on the solenoid. What happened when the solenoid was connected to the battery? When the solenoid is connected to the battery, current flows through the wire. This creates a magnetic field, and since the paper clip is made from magnetic material, it was attracted to the electromagnet. What safety advice did she give you? Well, as there is only a wire connected to the cell, a large current can flow. Why is there a large current? Because the resistance of the wire is low. This large current means there will be heating in the wire. As the wire can get hot, the solenoid should be disconnected when not in use. Okay, so the large current will flow through this wire. That means that the wire is going to get very hot, so we should disconnect or switch off the solenoid. The current in the solenoid when we're not using it. And then finally, she talked about different things you could test in an experiment, predict what would happen, increasing the current, increased number of turns on the coil. So for increased current, that means there would be an increased or stronger magnetic field. That means more paper clips picked up. So that's what we expect to see. We think that if we increase the current, there will be a stronger magnetic field, so we'll be able to pick up more paper clips. And then increased number of turns. Again, we expect that this will give us a stronger magnetic field. Why will it give us a stronger magnetic field? Well, if we go back to the diagram where we drew the magnetic field of the solenoid, if I've got more of these wires, that means I've got more of these arrows all going in the same direction. So I've got more arrows adding together, so I'll get a stronger magnetic field. And again, more paper clips picked up, because the magnetic field will be stronger. Okay, and now we've got some questions to answer, just to check what we've learnt so far. What happens in an electromagnet when current flows? When the electromagnet is switched on. When current flows, a magnetic field is produced in the electromagnet. So the electromagnet becomes magnetic. What happens in an electromagnet when the current doesn't flow? The magnetic field disappears. So the electromagnet is no longer magnetic. So if you imagine we had our paperclip experiment, here we've switched it on, current is flowing, the electromagnet picks up several paper clips, we disconnect the electromagnet from the power supply, the magnetic field disappears, it's no longer a magnet, so the paper clips then fall away from the electromagnet, fall onto the table. Which electromagnet has a stronger magnetic field and why? So it's identical circuits. We've got a cell and the solenoid. This is the symbol for the solenoid. So we have here the cell connected to the electromagnet. So there's current flowing of 1 amp. So this will create a magnetic field. Exactly the same here, except this time it's 3 amps. So the answer is B, because so B will have a stronger magnetic field because the current is larger. That's 3 amps compared with 1 amp. Now I complete the sentence. An electromagnet can be made stronger by, well, these are the 3 things we can do. We can increase the current. That will make it stronger. We can increase the number of turns in the solenoid. And the third thing we can do is we can use an iron core. So by adding a non-magnetic material in the center of the electromagnet, that becomes an induced magnet and adds the strength of its magnetic field to the magnetic field of the solenoid. So those are the 3 things we can do to make an electromagnet stronger.